The overall viewpoint among most researchers is that the ebb and flow hypotheses regarding the universe's starting points continue to be the essential explanation for its beginning phases of development. This hypothesis associates the development of stars and planets, which ultimately led to the rise of life, including humans. In spite of its impossible-to-miss name, the theory of prehistoric cosmic detonation offers a careful understanding of what might have happened at the universe's commencement. At the outset, the universe was restricted to an extraordinarily small space, much smaller than a pinhead, filled with particles. From this thickly packed state, a huge explosion of energy and matter, referred to as the Big Bang, erupted. This catastrophic event, which happened billions of years ago, started the sweeping advancement of the universe. Anyway, as scientific knowledge advances, irregularities have arisen, scrutinizing the suppositions supporting this hypothesis. When NASA launched the James Webb Space Telescope, JWST, the largest and most advanced space observatory ever built, specialists speculated that it would support the theory of prehistoric cosmic detonation. Anyway, only 1 year into its operation, the telescope surprised researchers with its remarkable capacity to observe the distant past of the universe. The JWST's extraordinary capabilities have revealed galaxies from such an ancient period that they challenge our current understanding of the universe's beginnings. This discovery has started an intense debate about the possible existence of matter that originated before the Big Bang. A crucial revelation happened when cosmologist Rohan Natu, analyzing data from the telescope, identified a system that existed shortly after the Big Bang, making it the farthest world seen to date. This discovery sent ripples through established researchers, highlighting the enormous influence of the JWST. The telescope's tremendous potential to reshape how we might interpret the universe is beginning to unfold, offering significant insights into the universe's earliest minutes. This period, loosely associated with earlier infinite events, is crucial to understanding the formation of the first stars and galaxies. The JWST's discoveries have gone against previous models by revealing galaxies with features that challenge prior assumptions. The flood of discoveries regarding early galaxies has sparked a frenzy among researchers, pushing them to reconcile these new findings with established theories. As scientists continue to explore, they face major questions about the nature of the universe and the forces that shaped its development. Notwithstanding its scientific progress, the JWST is strategically located 1.5 million kilometers from Earth, safeguarded from interference and cooled to nearly absolute zero by its sunshield, which is the size of a tennis court. This position allows the telescope to capture unobstructed views of the universe, unaffected by Earth's atmosphere. Equipped with a massive primary mirror and advanced instruments, the JWST was designed specifically to gather information about the early universe, which was previously inaccessible. This early cosmic time, known as the Great Dawn, began roughly 200 to 300 million years after the Big Bang, marking the formation of the first stars and galaxies. The mechanisms behind this process remain an active area of research, with various hypotheses exploring the roles of dark matter, dark energy, and the interactions between gas and dust and star formation. The JWST's ability to observe galaxies from this pivotal period provides an excellent opportunity for astronomers to test their current models of the universe. By studying these ancient galaxies, scientists can either confirm existing theories or uncover gaps in their knowledge, potentially leading to groundbreaking discoveries. Initially, the JWST was expected to identify a few weak, small galaxies during its early observations. However, the results far exceeded these expectations. The telescope's first images of the distant universe revealed a staggering number of galaxies with varying ages, sizes, and luminosities, far more magnificent than what had been expected. This unforeseen flood of early galaxies has led to a race among astronomers to redefine the record for the earliest known massive galaxies. New discoveries are continually emerging, leaving even experienced researchers in awe. Following the JWST's discoveries, both scientists and the general public have become eager to examine the characteristics of these advanced early galaxies. Some scholars have suggested that possible errors in how the telescope interprets large-scale observations might explain some of these remarkable findings. However, the prevailing view is that these discoveries represent a significant shift in how we understand the early universe, offering an exciting glimpse into how much more we could learn. The new revelations of early galaxies made possible by the JWST have raised significant questions about the nature of the universe, challenging traditional cosmological models. While some researchers are investigating whether these findings can be integrated into existing theories, others argue that they might point to a far more complex and strange universe than previously imagined. The fundamental question that remains is how the universe we know today arose from the turbulent upheaval of its early stages. The JWST's early discoveries could radically reshape our understanding of the Big Bang, providing new insights not only into distant galaxies and ancient cosmic structures but also into the very fabric of our own Milky Way galaxy. As Mark McFadden, senior researcher for science and exploration at the European Space Agency, aptly stated, "You build these machines not to confirm theories, but to break them. You simply have no idea how it will break." The origins of the JWST trace back to 1985 when the Space Telescope Science Institute, STSCI, began laying the groundwork for a successor to the Hubble Space Telescope. At that time, G. Weir, the head of STSCI, was tasked with envisioning what could come after Hubble. Despite early skepticism, Weir and a small team began developing what would eventually become the James Webb Space Telescope. Unlike Hubble, which primarily observes visible light, the JWST was designed to observe in the infrared range, allowing it to peer deeper into the universe. This infrared capability is crucial for studying distant galaxies whose light has been stretched into the infrared due to the universe's expansion, rendering them invisible to telescopes like Hubble. Equipped with its massive, cold, star-like mirror, the JWST has become an invaluable tool for unlocking the secrets of the Great Dawn. The need for such a telescope became evident in 1995, when the Hubble Deep Field Observation revealed an immense number of galaxies in a region of the sky previously thought to be empty. This discovery highlighted the richness of the early universe and underscored the need for a more powerful telescope capable of observing even further into the universe. After years of development and an investment of approximately $1 billion, the JWST was successfully launched on December 25, 2021. By July 2022, it was ready to begin its crucial year of scientific observation. Programs like the Early Release Science Centers and the General Observation Program were specifically designed to search for early galaxies. While initial expectations were modest, the results far exceeded these projections. The JWST's observations have already begun to challenge existing models of the early universe, uncovering galaxies that defy conventional cosmological assumptions. These unprecedented discoveries highlight the importance of pushing the boundaries of scientific inquiry and demonstrate the remarkable capabilities of cutting-edge technologies like the James Webb Space Telescope. As scientists continue to analyze data from the JWST, new insights may emerge that further test and expand our understanding of the universe. Cosmologists enthusiastically anticipated the outcomes. Numerous researchers had spent years setting up their data analysis systems for this moment. Instead of following the traditional peer review process, which can take months, experts chose to share their findings on preprint servers, such as AR-14, where papers can be freely accessed before undergoing formal review. This approach allowed for fast feedback and discussions through online platforms like Twitter, where established scientists could quickly engage in discourse about the findings. Rohan Nata referred to this new process as science by press release, and the ensuing wave of discussion was both intense and unprecedented. However, concerns arose about the possible downsides of the rapid dissemination of results. Klaus Pontoppidan, a JWST project scientist at STSCI, cautioned that while quickly sharing discoveries enabled fast communication, it also risked overwhelming the scientific process. The accelerated spread of discoveries, especially from such a groundbreaking mission, introduced challenges to traditional scientific workflows. Despite the rapid data release, the general consensus among most experts is that the current theory explaining the universe's origin remains fundamental to understanding its earliest stages. This theory suggests that the formation of stars, planets, and ultimately life, including human existence, is an essential part of the universe's development. Despite its unusual name, the Big Bang theory provides a coherent explanation of the universe's origins. In its earliest moments, the universe existed as an incredibly dense point, far smaller than the tip of a pin, filled with tightly packed particles. From this state, a massive release of energy and matter, the Big Bang, occurred, setting off the forces that would shape the universe. This immense event, billions of years ago, marked the beginning of the universe's unfolding story. As scientific data continues to evolve, however, inconsistencies have emerged, challenging long-held assumptions. When NASA launched the James Webb Space Telescope, JWST, regarded as the largest and most advanced space observatory ever built, experts expected its observations to confirm the Big Bang theory. Yet, in just 1 year of operation, the telescope astonished scientists with its ability to peer deep into the universe's past. The JWST's extraordinary capabilities have revealed galaxies dating back to an era so ancient that they force scientists to reconsider what is known about cosmic evolution. This discovery has sparked debates regarding the possible existence of pre-Big Bang matter. A significant breakthrough occurred when cosmologist Rohan Natu, analyzing data from the telescope, identified a galaxy that formed shortly after the Big Bang, making it the farthest observed galaxy to date. This finding sent shockwaves through the scientific community, highlighting the JWST's immense ability to reshape our understanding of the universe. The JWST's potential to revolutionize our knowledge of the universe is beginning to unfold, offering profound insights into its earliest moments. This time period, loosely connected to past cosmic events, is crucial for understanding the formation of the first stars and galaxies. The telescope's discoveries have challenged existing models by revealing galaxies with features that exceed prior expectations. This concentration of early galaxies has sparked a surge of scientific inquiry, prompting researchers to reconcile these new findings with established theories. As they continue delving deeper into these discoveries, scientists face fundamental questions about the nature of the universe and the forces that shaped its evolution. Despite its scientific advancements, the JWST's position in orbit, 1.5 million kilometers from Earth, allows it to operate without atmospheric interference. The telescope is shielded by a sunshade the size of a tennis court, ensuring it remains cool to nearly absolute zero, which is essential for its infrared observations. This strategic location enables the JWST to observe the universe with unparalleled clarity and precision. The telescope's design, including its large primary mirror and state-of-the-art instruments, is tailored for studying the universe's earliest stages, particularly a period known as the Cosmic Dawn. This era, which occurred approximately 200 to 300 million years after the Big Bang, marks the emergence of the first stars and galaxies. The mechanisms behind this transition remain an active area of research, with various theories exploring the roles of dark matter, dark energy, and the interaction of gas and dust in star formation. The JWST's ability to observe galaxies from this formative period presents a crucial opportunity to test existing cosmological models and potentially uncover new insights that could redefine our understanding of cosmic evolution. Initially, astronomers expected the JWST to detect only a few faint, distant galaxies. However, reality has far exceeded those expectations. The first images from the telescope revealed an astonishing number of galaxies of varying sizes, ages, and brightness, far surpassing predictions. This unexpected abundance of early galaxies has sparked a race among scientists to re-evaluate our understanding of the universe's infancy and determine just how far back in time these ancient structures extend. As new discoveries are made, the scientific community is continuously adapting to fresh insights, with both experts and the public eagerly awaiting further findings. Some researchers have speculated that a few of these early revelations could result from misinterpretations or errors in the telescope's measurements, as it is still in the early stages of its operational life. Despite these concerns, most experts agree that these discoveries represent a paradigm shift in our understanding of the universe. They provide a glimpse into a previously unseen cosmic past. The JWST's revelations about early galaxies have raised profound questions about the nature of the universe itself. They challenge existing cosmological models and introduce new complexities that may require a fundamental reassessment of our understanding of cosmic history. At the heart of these discoveries lies the question of how the universe, as we know it today, emerged from the chaotic events of its earliest stages. The JWST's observations of ancient galaxies offer clues that could dramatically alter our comprehension of the Big Bang. These new findings not only provide insight into the formation of galaxies, stars, and other cosmic structures but could also shed light on the composition of our own Milky Way galaxy, expanding our understanding of its origins and development. Mark McCaffrian, Senior Advisor for Science and Exploration at the European Space Agency, captured the essence of scientific discovery with his remark, "You build these machines not to confirm theories but to break them. You simply have no idea how it will break." His statement underscores the unpredictable nature of scientific breakthroughs and highlights the excitement and uncertainty inherent in this new era of space exploration. The JWST's origins trace back to 1985 when the Space Telescope Science Institute (STSCI) began conceptualizing ideas for a successor to the Hubble Space Telescope. Garth Illingworth, the head of STSCI, was tasked with envisioning what could come next after Hubble. Although initially met with skepticism, Illingworth and a small team persevered, ultimately developing what would become the James. Unlike Hubble, which primarily observes visible light, the JWST was designed to capture infrared light, allowing it to peer deeper into space. This capability is particularly crucial for studying distant galaxies, as their light has been stretched into the infrared spectrum due to the expansion of the universe, making them invisible to telescopes like Hubble. In 1995, the Hubble Deep Field Observation revealed an abundance of galaxies in a previously overlooked region of the sky. This discovery emphasized the vastness of the early universe and demonstrated the need for a more powerful telescope. After decades of development and a budget of approximately $10 billion, the JWST was successfully launched on December 25, 2021. By July 2022, it began its scientific observations, aiming to explore the universe in ways previously unimaginable. Programs such as the Early Release Science (ERS) initiative and the General Observer (GO) program were specifically designed to search for early galaxies. While initial expectations were cautious, the results have exceeded projections. The first images revealed a surprising number of galaxies from the early universe, challenging existing models of cosmic evolution. These discoveries have paved the way for innovative approaches to understanding the origins of the universe while reaffirming the importance of pushing scientific boundaries. As the first data from the JWST arrived, cosmologists eagerly anticipated the results. Researchers had spent years preparing for the telescope's observations, and the excitement was palpable. Instead of following the traditional peer review process, which can take months, the scientific community chose to release preliminary findings on open-access preprint servers, such as AR-14. This allowed for faster dissemination and public discussion of the results, enabling experts to engage in real-time debates via online platforms like Twitter. Rohan Natu referred to this phenomenon as science by press release, acknowledging the unprecedented speed at which information was being shared. However, some experts, including Klaus Pontoppidan, expressed concerns about the rapid spread of unverified findings. While the fast exchange of ideas fostered collaboration, it also posed challenges to the scientific process. Despite these concerns, the prevailing view among most researchers is that